Thank you. I want to talk about just a little bit of work that we've been doing over the last several years on devices that we hope are useful for quantum information processing, in particular quantum computing, according to a certain scheme. There's an awful lot of backstory, so I'll go kind of fast through some of these slides. Not to worry, I have an exit strategy. When she says it's 5 minutes to go, I'm going to go to slide 38 no matter where we are before then. So I'd like to acknowledge several of my important collaborators. You can see some folks from here at RIT, Paul Alsing from the Air Force Research Lab. I'm pretty sure that's not the AFRL logo, but it turns out that Paul and I both graduated from the Harvard of the Ozarks, the University of Arkansas, so I thought I'd throw that up there. And several RIT students have helped us along the way, and this is not a complete list because I have some new students who are just starting up now. And I really appreciate all the work that we've done together. So if we could do this, okay, if it was possible to find a nonlinear interaction that would allow you to have perfect photonic control of a photon, you could build something like a C0 gate, and smarter people than me tell me that if you could do that, you could do universal quantum computing. Problem is, there aren't any things in nature that people found that have nonlinearities large enough to make this feasible or scalable. So another approach is to look at so-called linear optical quantum computing, and this is necessarily a probabilistic idea, meaning the nonlinear thing, the thing on the previous slide, that would obey a Hamiltonian. You could solve the Schrodinger equation for it, and you would have quantum computing deterministically. You have to sacrifice that in order to kind of get at the sorts of I'll call it pseudo-nonlinear interactions that you need for something like a C0 gate. This is what I'm going to be talking about today. Our scheme is based on this idea here, specifically this thing. So I'll say more about that as we go forward. Just as an example, this is a schematic diagram of something called the Hong-O-Mandel effect. I'm sure lots of you have heard of it. I argue, I'm not the only one, but this is sort of an example, a simple example of so-called measurement-induced nonlinearity, meaning if you send two photons into a 50-50 beam splitter, it'll turn out that if they arrive at exactly the same time, that you'll get an output state, this state vector, that when you measure the photonic output, you'll never get a coincidence in those two detectors. Meaning you'll either measure both photons to go one way or both photons to go the other way. That bunching, taking two individual photons as input and getting two one way or the other, that's kind of a nonlinear process if you think about it. You're herding together photons where they wouldn't ordinarily like to go. So the deal is that you get that to happen, but when you do a measurement, of course, you're going to select either that branch of the state vector or that branch when you do a projective measurement. And that means that you're going to get this bunching, but you're only going to get it half the time. So what you gain is a sort of effective nonlinear interaction, and what you lose is 100% reliability of it. So in some situations, that's a good trade-off. And I want to try to describe one of those situations today. So just a basic outline. You'll see this again. I won't dally on it. So the overall goal, this is the pie in the sky thing that many of us are working together to try to have happen, is to have integrated quantum circuits and photonic sources and detectors on a chip, tiny little microchip, in such a way that it's scalable enough that you can make a practical quantum computing system or a quantum information processing system out of it. What I'm going to talk about today is specifically this part of this pie-in-the-sky dream chip that we'd like to be able to design. Stefan Preble, who's one of my close collaborators, they've made a lot of advances in several aspects of these chips, and I'm sure you'll hear more about that today and tomorrow and Friday. So this is the obligatory fabrication slide. Here's how I like to explain this slide. Mind you, I'm a theorist. I do calculations. So it's my understanding they start out with a material like silicon, which is what our waveguides are made from. Then they do this, and then later they do this, And then later they do this, see where I'm going with this? And then later they just, here though, some sort of factioning develops in the lab, so some people resist developing this thing any further. Fortunately, they're able to resolve this shutdown and proceed with in other words, I don't know what any of this means, but all I know is that I have friends and collaborators who can do this, and that's good because the things we do with it are quite useful, I think. This is the way I understand it. Apologies to anyone who's worried about the second quantization of this, but in my life what's happened is grad students and postdocs will disappear from here without a device, and then a little while later they come back with a device. So what I've done, what I've mostly worked on is the modeling and the calculations in terms of the input-output characteristics of this class of device. And so really the question is a simple one. We're going to send photons in, and we want to know what comes out, because if we understand for a given input what comes out, perhaps we can use that to engineer something that's useful, like a CNOT gate or something. So linear quantum optics on a slide. This is an oversimplification, but the basic idea in that's going to impact the work that I've done along with my collaborators is that in general linear quantum optics, what happens is you send a couple of photonic modes into some kind of mystery 2 in, 2 out device, and then photons come out of it. And it's linear quantum optics, so we can actually use the rules of quantum optics to figure out how the output operators are related to the input operators. And that's a simple thing, and it's the kind of thing you'll see in textbooks. And the idea here is if you can relate the output creation operators, C dagger and D dagger, to the input creation operators, then you could start with an input state that you excite out of the vacuum, make direct algebraic substitutions here, get this horrible binomial mess, and you could in principle figure out what comes out. So it's a simple idea. For experts in the crowd, what we're doing here is essentially assuming we're working in the Heisenberg representation. The idea being that the transit time across any of these SU2 devices is really, really, really small because light is really, really, really fast. So back to this picture. This is a proposal for the so-called Nil-Laflamme-Milburn CNOT gate. It's a probabilistic device that does, when it works, it does reproduce the truth table for a controlled knot operation, which is what one would need for universal quantum computing. And it functions such that it works 1/16 of the time. So the probability of success of this thing is 1/16. That might sound bad, but it's better than 0, and we can work with that, assuming a couple things are true. This is a sort of an informal list of the so-called DiVincenzo criteria for quantum computing. If you look at 3 different lists, you might find it written down in 2 different ways. What I'm really looking at here is this idea of scalability. Because of course, if you have something that works 1/16 of the time, and it's scalable, then you can make enough redundancy in that thing so that you can get it up to a level where you can apply the methods of quantum error correction to make something that's actually reliable. Right? I am not one who does quantum error correction. I'm saying that because that's what people who know about that have told me. But it makes good sense from an engineering perspective that if you have something that works only some of the time, make several copies until you can use redundancy to solve the problem you're trying to solve. You'll notice this thing is fraught with all kinds of these SU2, the 2 in, 2 out circuit elements, mainly beam splitters in this case. So the idea is that if we can find something, some sort of a scalable substitute for the beam splitter, especially if it has nice properties like I want to show you, we might be in business if we could actually design. So adapt the Nil-Laflamme scheme to the KLM scheme to the case involving ring resonators rather than just beam splitters. And that's the deep thought behind anything that I'm going to tell you. It's not anything really magical. The deal is, though, if you actually do this with bulk optics, it's the size of an optical table and it's a huge mess of detectors. It's fundamentally not scalable. It's good for proof of principle, and that experiment's been done. It just isn't the kind of thing that you could expect to use in a practical computing device in this form. So what we decided was the following. We decided, well, everywhere we see one of those beam splitters, not quite everywhere, but that's a technical point, but for most of the beam splitters, what we want to do is substitute in our, what we're proposing to be the fundamental circuit element for silicon nanophotonic quantum information processing networks. And it's this thing. It's a double bus, directionally coupled micro-ring resonator. Here we have a couple of waveguides. Here's our micro-ring resonator. We have input modes that are described by boson operators A and A dagger, and F dagger, and output modes C and C dagger and L dagger. Okay. Advantage of this thing is that these things, because they're printed in silicon, according to the fabrication process that I've already explained at length, they are scalable, and they're actually rather, I guess, easy to produce. Stefan has been doing this for years. So what we want to do is we want to try to see, well, I mean, how would we analyze the input-output characteristics of this thing? I mean, how do we relate the input, the output, and the input? And what, if any, advantages might it offer? So just a couple words on the theoretical formulation of these things. This was really like this I think is why Stefan and Paul and those guys keep me around. So what we did was we applied a sort of an idea that's related to Feynman path integrals to how we analyze these devices. And so the idea is what we did was we just simply constructed a transition amplitude for every possible way you can get through the device. So in other words, if you think about, there really are four things we have to worry about. If you send, say, a photon in along A, where could it wind up? And the answer is it could wind up either at C or at L. And if you send one along F, the same thing is true. It could either wind up at L or at C. What makes this device a little bit trickier than, say, just a beam splitter like you'd find in a textbook is that there are several different, if you will, Feynman paths through this system. In other words, A could get to C by a direct transmission through that coupler, or it could make a round trip through that coupler, or it could make 2, or 3, or 7, or 1,000,000, or however many. And according to this notion about constructing, constructing the actual input-output relationship, we'd have to worry about a single transition amplitude for every one of those possible paths. So these little phi's with the subscripts here they represent an individual thing that could happen along the way. In other words, this might be a phase shift, and that might be one of those cross couplings, the kappa in this, the kappa or the gamma. The tau and the eta are the direct transmission amplitudes. And you just follow through every single one of these possibilities. Then you add up all of the possibilities along all the paths connecting any one initial, so like mode A, with any one final, like mode C. And then if you wanted to try to figure out what's the state vector coming out of, say, mode C, you'd use the propagator constructed according to the sum over paths, and you would just simply apply it to the initial state as so, or for every possible initial state like so. So that's what we did. These are the Feynman rules adapted to this kind of linear optical calculation. I do want to point out that these are mathematically mythical, right? This is probably not legitimate mathematically. It works as a practical calculation tool, but certain things here, we're just imagining that we have these little balls of light that we're calling photons, which is a myth, and we're also imagining that those are described by annihilation operators, which is also a myth. I mean, not that they're described, but they are literally directly represented by them. They're not the same thing. But we're going to apply that propagator technique to that thing. So the only reason why we do this is because you can show in any case of interest it actually works if you interpret things this way. So we interpret photons in a certain way in steps 1 through 4 to get the propagator, and then we uninterpret the photons and turn them back into boson operators, and that actually produces the result that we want to get. And by the way, there are other people who thought this up also. So just as an example, if you think of a simple phase shift, this is the version that you'd be familiar with from applying kind of the Heisenberg picture to a phase shift. That's what happens to an operator when it goes through a linear phase shift theta. That shift is generated by the photon number in that mode. And so the actual effect is to take the input operator and multiply by the phase factor you'd expect. What we're doing is interpreting this phase factor as a transition amplitude, basically. So, the couplers we deal with, there are two options. You could have a cross-coupling from mode A into mode D in this picture, or you could have a direct transfer coupling from mode A to mode C. Of course, there are reciprocity relationships that force things like the commutators to remain true, the bosonic commutators to hold on both sides. So if we were to construct a table of the various different transition amplitudes through this coupler, then we'd get those four options. It's exactly the same as a beam splitter. If you like fancy mathematics, you can think of, in the Heisenberg picture, you'd think of rotations of the two-mode operators generated by these two effective angular momentum operators, but we don't need to go there. So here it is. The ring, we enumerate the paths through the ring, and you can see what happens. I made a table summarizing this. I'm not going to go through the whole thing, but you have to keep track of the various numbers of round trips, and this is everything that can happen along a round trip connecting a particular input with a particular output. What you do is to get the correct form of the mode, the operator in mode C, the bosonic operator for mode C, you just sum over all the paths that connect A and C and multiply by A, and then you sum over all the paths that connect F and C and multiply by the F operator, and then you got it. And the result looks sort of like this. Again, I'm going fast through this. The details are really not so important. But the point is, we get something that has a fairly rich structure to it. So so we get what we might think of as effective transition probability amplitudes and effective cross-coupling amplitudes. Same thing as a Fabry-Perot. You can do the same thing with the well-known Fabry-Perot Etalon. Same analysis. This is there just for sanity check. We can even model losses. So the way you model losses in a double bus ring is you pretend that one of these buses is actually a loss channel. That means that we don't know the actual output state there. And in quantum mechanics, when you don't know the output state someplace, what you have to do is construct a density operator rather than just a state vector for the system. And you have to trace out those modes that you don't know. And as it turns out, if we do this, we were able to reproduce some results that Yariv had in a paper from many years ago. And in fact, if you imagine putting in coherent states to try to mimic the classical case, it's a nice sanity check in that we can actually derive one of Yariv's sort of empirical parameters, the so-called circulation factor, and it turns out the circulation factor is related to the probability of a transfer, of a direct transition inside the ring right up here. And that kind of makes sense, because if the circulation factor ranges between 0 and 1, and so if it's 1, you get pure circulation and therefore no loss. If it's 0, you get complete loss. And so this eta parameter is the thing that's going to govern whether something actually stays directly in the ring for another round trip, or whether it leaks out through the loss channel. So that was an encouraging result from some years ago. So here again, the reason why we focus on this particular circuit element is because it has a rather surprising advantage when it comes to the Hongo-Mandel effect. And the Hongo-Mandel effect, as you might be aware, is something that's sort of it's kind of in the guts of a lot of quantum information processing schemes. So the idea of the Hongo-Mandel effect is, again, at 50-50, you get that noon state that comes out where you have photons that you'll detect either both in one channel or the other. And the fidelity of that state is exactly 1, only at exactly the 50-50 point on this beam splitter. And if you're willing to relax it a little bit, and you look at this, like I labeled, this is kind of this is the transition parameter. So if you're at the 50-50 point, 1 over the square root of 2, you get exactly the Hongo-Mandel effect. If you're willing to accept 99% fidelity, you get a little bit more of a range to work with, but not much, and so on for 95% and 90%. As it turns out, with these ring resonators, the Hongo-Mandel effect is something you get whenever this condition, this constraint, is satisfied. Okay? This is the thing that makes photon coincidences go to 0 for any value of these parameters. And you can tell here there are a bunch of parameters here that we have to adjust. So I just got the sign. So that means that we actually get the Hong-El-Mandel effect on entire manifolds. This is a one-dimensional case, so anywhere on this curve, the Hong-El-Mandel effect will occur. So basically, it's just a bigger target. In other words, we have a lot more of parameter space where we could work to get the Hong-El-Mandel effect, which relaxes some of the engineering constraints that you would have to have on a device that relies on the HOM effect. This is just to illustrate that, you know, we also have this ability to thermally tune these circuits so that if you have a device that isn't quite doing what you want it to and you need to get it back on one of these Hong-El-Mandel manifolds, it's experimentally feasible to actually adjust it in situ to do that, which was an unexpected advantage to looking at these ring resonators. And this is just the same thing in 2 dimensions, so I'll move along. This is a matter of human convenience. It turns out that because these things are directional, we're going to have photons coming in this way and in that way. When human beings multiply matrices, we like to look at something over here and multiply the matrix from this one by the matrix from this one and get the output. It doesn't work out that way because of the topology of the situation. So what we do is we swap some of these modes around. We just swap the independent variables until we get the independent variables out of one of the rings to line up with the ones that at the matrix level would be the inputs for the other one, even though the photons might be going the opposite direction from what you might want them to. In your mind, you might want them to. They're going the direction they do. This is not hard to do. It's nth grade algebra where n is less than or equal to 8. What you do is you just literally rearrange things so that you get the outputs where you want the outputs and the inputs where you want the inputs. The rule for doing that is that you get these brand new matrix elements when you do those mode swap operations. So if you want to switch the upper rail, so C out for C in, you would do this kind of operation. You would just replace all the ABCDs with the primes. If you want a lower rail swap, it's just the double prime operation. The matrices that we need to deal with in the device we want to look at. So this is the thing we propose as a nonlinear sign shifter, like the guts of that Nil-Laflamme-Milburn scheme. And so this is just the three-dimensional, the 3x3 version of these mode swaps. I'll say another thing about that in a moment, so I'll skip that. So this is the thing. This is what we're working on. We're trying to take this big clunky bulk optics nonlinear phase shifter that you need for the CNOT gate. It's one of the crucial ingredients of that, and replace it with this nice scalable version of the device based on ring resonators. So if you look at this up close, we find we have lots of adjustable parameters here. There are the round trip phase shifts for each of the rings. There are the couplings between the rings and the waveguides. There are inline phase shifts that are available to us. The long and the short of this is that we did a lot of, so the way the nonlinear phase shifter works is that it actually just switches the sign of this 2-photon component in the CNOT gate that I showed you earlier. The reason you want to do that is you want to use destructive interference to kind of get rid of any of the 2-photon components in the device. Because those devices they're one photon interacting with another. So if you get them to bunch up when you don't want them to, that's a bad thing. So the nonlinear sign shifters are there to try and make sure that doesn't happen. So what it does is this. How it does this is you imagine unitary evolution through the system, and then and that'll produce a state that has the desired output that you want plus a component that's orthogonal to it. What we have to do then is a projective measurement to select off the piece of this that is desirable for the CNOT gate. And when you do that, that's when you're turning this from a deterministic system to a probabilistic one. It turns out that happens with a probability of this beta squared, this beta squared. And you can actually show that the probability of success of this device is actually that beta squared. So what we did was we solved for the unitary part using that path integral formulation appropriate to this network. Then we do the mode swap stuff to get everything lined up the way we want it lined up so we can actually get something that you can encode into a computer easily. And then looked at the branch of the state vector which is actually desirable to the nonlinear phase shifter. Whoops, wrong way. And so as it turns out, even under conditions where, this is a simple example where all 3 rings are on resonance and all 3 phases are set to 0, And so it turns out that these families of curves for the tau, we plotted tau squared and eta squared, because those are the things, those are the transition probabilities that would be more relevant to device design rather than just the amplitudes. And as it turned, and the long and the short of it is, for any points on these curves, so this black curve, that corresponds to both rings 1 and 3 because they turn out to be symmetric here. And the dashed curve is for ring 2. For any choice of parameters on these curves, you get optimal nonlinear sign shifting and therefore a viable C0 gate. So just a higher dimensional example. This is the buzzkill slide where we've also analyzed the way these manifolds behave when you include things like losses, and we've also analyzed ideas like photon generation in these rings, which is also important for another phase of our dream chip. There are the references there. So, and with that, I'm over time already, so I'll stop.
We have time for a couple of questions.
So it's 1 over 4. So it's in every way just like the bulk optic Nil-Laflamme mill. So essentially what we did was we took what they're doing and thought, wouldn't it be great if you could scale that? And so we tried it with these fundamentally scalable elements. And of course you can get situations where you get success probabilities that are less than 1/4. But we've focused on the ones that are 1/4 because that's the theoretical maximum for those things. So.
So could you elaborate a bit more on the losses? Presumably, you just increased your path length for the photon. Qualitatively, what is the difference between, say, a fractional coupler loss and your proposal for a ring?
I guess I'm going the wrong way, sorry. This is the double bus ring, the initial thing that I showed, the Hong-Mandel thing. So you could imagine that this kind of degradation would occur. So this is based on something that's effectively the Areve circulation factor. So as we back those down from 1, where you get nice Hong-Mandel surfaces, they start to break up and fragment, and so obviously there are fewer combinations of parameters that work for what we want them to work. When we did this, we really just applied what it boiled down to was essentially you apply the Langevin theory of losses and find out that you get exactly the same results as if we had done that directly. We actually formulated it a slightly different way, and so I don't know that I'm answering your question, but of course the more stuff you put in the circuit, this just compounds because as you said, you have more optical path length there. So I don't know if that's clear or not. Yeah, sure.
One last question over there.
Are there types of errors that are unrecoverable in this type of system, like tuning kind of perspective?
I'm not really one to comment on the error correction aspects of it. I make errors.
Error correction just in the physical implementation of the device. Like if your coupling coefficients are off, are there types of errors like that you can't recover by like thermal tuning of the elements, for example?
My guess is that yes. I mean, if things are just too far off, you can only thermally tune so much. But I'm not the person to really. I don't know numbers and figures about that. So. When we designed this, we actually designed several of these circuits, and we're going to do some experimental tests over the summer on these things. And so, of course, when you design them, you have to try to get them literally close enough for government work, Air Force lab. And so I just sort of understand that to mean that if they're too far off, then you can't do anything to save them. But I am by no means an experimentalist. Yeah. Yeah, essentially it's a bigger target, so that we expect that to be an advantage. But whether there are areas that are unrecoverable, I don't think we've really even analyzed that. So.
Let's thank Ed once again.
Thank you.